All right, let's quickly go over some things called universal gravitation. So it's not just 9.8 any longer. I know, just when you thought gravity was 9.8, we got to change it up on you. And the reason why is because gravity doesn't just exist on Earth. Gravity exists in lots of places. And so when we talk about the universe as a whole, then gravity becomes a little bit more complicated. And in some ways, it's actually simpler because we can describe it so that it's constant everywhere. So what we're going to try to answer here is basically what is the relationship between mass, distance, and force in what's called Newton's universal law of gravitation. We've had three of Newton's laws, Newton's first, second, and third. We had the inertia law. We had F equals ma. We had that every action force has an equal and opposite reaction force. And now we have Newton's universal law of gravity. And really not any new vocabulary here. So previously we went over like, what's my weight? Right. And again, in everyday language, mass and weight are pretty much interchangeable, but in physics and science, they're not. So previously we said our weight was the product of gravity pushing down on a mass. And we took Newton's second law, which is force equals mass times acceleration, and changed it up a little bit. Instead of the force, we have F with a little w. This W stands for weight. And then we change out the A to G for the force of gravity. So effectively, it's still the same as Newton's second law, but this is specifically for weight. And that's still going to be true. So we've been using this little g, lowercase g, and we've been using 9.8 meters per second or 9.8 meters per second for the acceleration of gravity on Earth. And so when we use little g, that was the acceleration of gravity. And we're going to introduce another thing today called big G, and the big G is not going to be the same as the little g. Little g is not constant. It's the acceleration for us on Earth. If we went to the moon, we went anywhere else, if we were weightless, then that G changes. And so what we're going to look at today is a uppercase G and talk about that being constant. So gravity is a universal force. It means that it's, as far as we know, it exists everywhere. And it exists between any two different objects that we have. And so the gravity that we have with us, between us and Earth, exists, but there's also gravity between the Earth and the sun, gravity between Earth and the moon, gravity between Earth and Mars. And so effectively every object has an attraction or pull on another object's. You and the person sitting next to you have an attraction of gravity between the two of you. We'll see in a moment why you don't really notice it. Mostly it has to do with your tiny, tiny size in the big scheme of things. But there is an attraction between all two objects, any two objects that exist. And typically, though, we only really notice them if it's a substantially large object, like the size of a planet or a moon or a star or something along those ways. Gravity tends to be a fairly weak force in nature compared to some of the other ones we have. So we have a formula on your formula sheet about how to calculate the force of gravity between two objects. And again, it looks like this on your formula sheet. It looks a little bit complicated. We could still calculate the weight of us with this, because we'll talk about what everything stands for in a minute. But effectively, if we know the mass of things and we know how far apart they are, then we can calculate the force that's going to be between them. But for our purposes, we don't really have to do a whole lot of calculating. We just need to be able to understand how each of these variables is going to affect the amount of gravity that there would be between two objects. You'll see in this formula that there is a big G, and we'll get to it in a minute, but it's also explained on your reference sheet that we have. F with a little g, that is the force of gravity. The M1 and M2 are the masses. D is the distance. And then we have this G, uppercase G, which is a constant. And again, this is on your reference sheet. It's 6.67 times 10 to the negative 11th, which is a really small number. And sometimes in science formulas, we have a constant to just kind of make sure, like without them, the formula doesn't quite work to give us the answer that we want. The main thing is, though, is it's not that we're messing around with the formula. It's just that the amount of force we'll see in a moment is related mainly to the masses and the distance. But to get an accurate force, we need this to plug in this G that's 6.67 times 10 to the negative 11, just to make the math work out. No need to really worry too much about what this is, what it looks like. If you don't understand it, that's probably okay. You'll probably be able to solve things quite effectively if you need to. All right. So what do we need to focus on? Here's the main things we want to focus on. The Fg is proportional to the mass, and basically each mass. And so M1 and M2, these are two different objects. And the idea is if one of those two got bigger, then your answer when you do the math is going to get bigger. So proportional means as one goes up, the other one's going to go up. And that is going to be the case because they're on top of the fraction. Distance, however, is inversely proportional because it's on the bottom of the fraction. If you make the bottom of your fraction bigger, you're going to correspondingly get a smaller answer. And so these are inversely proportional. As one goes up, as the distance increases, the amount of force is going to end up going down with that. So in summary, if you have more mass, we've got more gravity. If you've got more distance, you're going to have less gravity. And that's probably the main concept that we're going to have right here. In terms of the math, the main things that you're going to need to answer for us are to tell us what would happen if the mass or the distance got doubled or tripled or cut in half. What kind of an effect would that have overall? Now, some of us, again, you're pretty good at math and you could just figure it out. You could understand by looking at this formula that if you doubled one of the top numbers, then you're going to get a double for an answer over here. Or if you doubled both of the top numbers, then you'd be 2 times 2 and you might get 4 for that. Some of us are a little bit, less able to do the math in our head. And so one of the little tricks we can use for this is what we can call the law of ones or a rule of ones. To be able to figure out what happens if we do something to the mass or distance. Okay, so the way that this works is basically take your formula and plug a 1 in for everything. And this makes everything really nice and easy for us to compare with, because if we plug in a 1 for everything, our answer is 1. So big G is 1, both of our masses is 1, distance is 1, then the force is 1. That's basically how you start. And you don't really have to do this. You can just remember that if you plug a 1 in for everything, you're going to get a 1. So then what happens if you get a question? For example, what would be the result if the distance doubled? Well, then go back in and substitute. So where the distance is on the bottom, let's don't have a 1. If it doubles, let's call it a 2 because 2 is twice 1. And if we do the math for that, then the bottom part of this fraction becomes a 4. And lo and behold, we get an answer of 1/4. Therefore, if we double the distance, you're going to get 1/4 the amount of gravity. Nice and simple, right? So your answer is going to be 1/4, 1/4 the force. What if you had something like, what would be the result if each mass doubled? Well, go into your formula, and where the masses used to be 1, double them, turn them into 2s. And if you do the math, 1 times 2 times 2, you get 4. The bottom is still going to stay 1 because it's still 1. And we get an answer of 4. Compare that back to 1, it's 4 times as big. So if each mass doubled, we would end up getting 4 times the force, because when we change both of these numbers in, we would get a 4. So conceptually, this is probably the most math that you're going to need to do. We could go in and do math with actually plugging in actual numbers for all of these things and doing the math around and trying to figure out what the force would be. But in terms of assessments, we're most likely just going to be focusing on these types of things. All right. So in summary, all objects are going to have a gravitational force to other objects. We tend to not notice most of the time because we're so small. And again, think about the way that formula works. My mass on top of that formula is going to make a really, really tiny number. And so there's not, if my mass and your mass were both up there, the amount of gravity is going to be almost inconsequential or too small for us to even notice. So the force depends on the mass and the distance. The bigger the mass numbers are, like with 2 planets, you're going to get an actual large force. The distance is important. And again, as the distances get farther and farther out, like with our planets, Mercury, Venus, Earth, Mars, Jupiter, as you get farther and farther out, that amount of gravity is also going to decrease. So we get more mass with, we have more gravity if there's more mass. We have less gravity if there ends up being more distance. And hopefully we can use that rule of ones to be able to figure out how the force of gravity can change when the variables end up changing.